Quantum computing, a gateway to a new era of computation. Introduction. The world of technology has witnessed tremendous progress over the past decades. From the invention of digital computers in the 20th century to the rise of the internet and then artificial intelligence, each milestone has reshaped the path of human civilization. However, many scientists and engineers believe that what lies ahead may be even greater than previous revolutions. Quantum computing. Unlike classical computers, which operate on binary logic, 0 seconds and 1 second, quantum computing uses the fundamental principles of quantum physics to process information. In the quantum world, particles can exist in multiple states simultaneously, giving quantum computers exponential computational power. If classical computers drove the digital revolution, quantum computers may usher in an era where solving complex problems such as molecular simulation, new drug design, global supply chain optimization, and precise climate forecasting becomes possible. Problems that today seem unsolvable even with the most powerful supercomputers could potentially be solved in minutes with quantum computing. The importance of this technology is so great that nations and major corporations worldwide are investing billions of dollars in it. The race to achieve quantum supremacy, the moment when a quantum computer can solve problems beyond the reach of any classical computer, is in full swing. In 2019, Google claimed to have reached this milestone, though the matter remains debated and under investigation. Thus, quantum computing is not just an emerging technology, but also a strategic global battleground. Just as the internet transformed economies and societies, quantum computers may drive the next great wave of transformation. History of quantum computing. Origins in quantum mechanics. The theoretical foundations of quantum computing trace back to the early 20th century and revolutionary discoveries in quantum physics. In 1900, Max Planck introduced the concept of quantized energy. In 1905, Albert Einstein explained the photoelectric effect, showing that light consists of particles called photons. Later, scientists such as Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the core theories of quantum mechanics. These theories introduced phenomena like superposition and entanglement concepts that later became the building blocks of quantum computing. At the time, no one imagined these abstract ideas would one day lead to machines capable of transforming the future of computation. First ideas of quantum computation. In the 1980 seconds, physicists began exploring the potential application of quantum principles in computation. Nobel laureate Richard Feynman famously stated in 1981, "Nature isn't classical. If you want to make a simulation of nature, you'd better make it quantum mechanical." This marked the first serious conceptualization of a quantum computer. Soon after, scientists like David Deutsch at Oxford University developed early theoretical models and algorithms for quantum computation. In 1985, Deutsch published a paper proposing a universal model of quantum computing, showing it could outperform classical computers. Quantum algorithms. In the 1990 seconds, a breakthrough came. Peter Shor introduced an algorithm capable of factoring large numbers far faster than classical computers. This had strategic importance, as modern encryption systems, for example RSA, rely on the difficulty of factoring. Shortly after, Love Grover developed another algorithm for faster database search. These discoveries demonstrated that quantum computing was not merely theoretical curiosity, but a potential technological revolution. Experimental progress. From the late 20th century onward, research groups sought to build real quantum computers. Early devices had only a handful of qubits and were highly unstable. Progress accelerated in the 2010 seconds, with companies like IBM, Google, and D-Wave building prototypes. In 2019, Google announced that its 53-qubit computer solved in minutes, a problem that would take classical supercomputers thousands of years. Although we are still far from large-scale, fault-tolerant quantum computers, this short history reveals how quickly the field evolved from abstract theory to one of the most competitive arenas in science and industry. Scientific principles of quantum computing. 1. Qubits. the basic unit of quantum information, capable of representing 0 and 1 simultaneously. 2. Superposition. A particle can exist in multiple states at once, enabling massive parallelism. 3. Entanglement. Two qubits can become correlated regardless of distance, enabling powerful information transfer and processing. 4. Interference. Quantum waves can amplify correct computational paths and cancel out wrong ones. 5. Decoherence. Interaction with the environment can destroy quantum states, making error correction and isolation essential challenges. Quantum hardware. 1. Superconducting qubits, used by Google and IBM, scalable but require ultra-cold environments. 2. Trapped ions, high precision and stability, pioneered by IonQ, though slower and harder to scale. 3. Photonic qubits, use photons at room temperature, ideal for communication but hard to entangle. 4. Spin qubits, based on electron spins in semiconductors, compatible with silicon chip technology. 5. Hybrid approaches, experimental methods combining multiple techniques or novel materials. Quantum algorithms. 1. Shor's algorithm, efficient factoring of large numbers, threatening classical cryptography. 2. Grover's algorithm, faster search in unstructured databases. 3. Quantum simulation algorithms, model molecules and materials with unprecedented accuracy. 4. Optimization algorithms, QAOA, etc., solve complex logistics and resource allocation problems. 5. Quantum machine learning, harness quantum parallelism for faster AI training. Applications: cryptography and cybersecurity, breaks current encryption, driving research into quantum-safe alternatives. Medicine and drug discovery, simulate molecular interactions for new treatments. Materials science and energy, develop advanced batteries, superconductors, and sustainable materials. Artificial intelligence, accelerate machine learning and data analysis. Optimization, improve logistics, traffic systems, and supply chains. Finance and economics, enhance risk analysis and portfolio optimization. Climate and space science, enable accurate weather prediction and space exploration planning. Challenges and limitations. 1. Noise and decoherence. Qubits are fragile and require extreme conditions. 2. Quantum errors. Need for advanced error correction and redundancy. 3. High costs. Specialized, expensive infrastructure. 4. Talent shortage. Requires multidisciplinary expertise. 5. Lack of standards. Competing programming frameworks. Q-number, Qiskit, Cirq. Global competition. United States, leading companies, IBM, Google, Microsoft, Intel, and national initiatives. China, major investment, progress in quantum communication and prototypes. Europe, EU's quantum flagship program, €1 billion over 10 years. Other nations, Japan, Canada, Australia, and Israel with national projects. Startups, D-Wave, Rigetti, IonQ, PsiQuantum, exploring diverse hardware approaches. The future of quantum computing. 1. True quantum supremacy. Practical breakthroughs expected within 10-15 years. 2. Integration with AI, enabling ultra-fast deep learning and potentially superintelligence. 3. Advances in medicine and energy, personalized drugs, efficient batteries, new superconductors. 4. Ethical and security concerns, encryption breaking, privacy risks, and need for safeguards. 5. Cloud accessibility, quantum power available via the internet, not personal devices. Conclusion: quantum computing is more than a technological advance. It is a scientific and intellectual revolution. Built upon principles once thought bizarre and counterintuitive, it now stands ready to reshape humanity's future. From cybersecurity and medicine to energy and AI, no field will remain untouched by its impact. Yet, the path ahead is filled with challenges technical, ethical, and economic. Although practical quantum computers are still on the horizon, rapid progress suggests this future is not far off. Just as the internet transformed the world, Quantum computing may open the door to a new era of science and technology. Support us with your subscriptions, likes, and encouraging comments so we can keep creating with even more passion and purpose. Every thought you share means the world to us.